Picture this. It's like 2:00 a.m. on a Saturday.
Oh, the absolute worst time for anything to happen.
Right, exactly. So you're managing this massive AI data center, and you're at home, maybe asleep, and somewhere in the middle of just a massive row of matte black server racks, there's this microscopic stress fracture in a high-pressure coolant line.
Just waiting to snap.
Yeah, and it finally gives way. So liquid begins to spray directly onto a rack that contains literally millions of dollars worth of cutting-edge GPUs. Now, in a perfectly designed system, you'd want this immediate surgical response. But in reality, what actually happens in that control room is pure, unadulterated chaos.
Oh, it's an absolute cascade of noise. I mean, the moment that liquid hits the silicon, you don't just get one clean, polite alert that says, leak in rack 4.
Right, that would be too easy.
Way too easy. Instead, the network switch throws a critical error because data packets are suddenly dropping. The GPU starts screaming, literally throwing software alerts because their thermal limits are being breached.
Because of shorting out.
Exactly. And the main power distribution unit, the PDU, it detects an electrical short and starts throwing voltage warnings. So your inbox is instantly flooded with hundreds of automated emails from like 5 different monitoring tools, and they're all just flashing red.
Yeah, the dashboard lights up like a Christmas tree.
Yeah.
And you, the human operator who just got woken up, you're sitting there trying to play detective in the middle of the night.
It's a nightmare. You're trying to figure out, did the server crash because a developer pushed bad code?
Yeah.
Did the network switch just fail on its own? Or is there literal water pooling on the floor?
Right. And by the time you actually figure out it's a physical leak and you manage to manually cut the power, the hardware is totally fried. I mean, the damage is already done.
And, this isn't just a hypothetical. The sheer density of modern AI workloads, the incredible amount of power they draw, and the massive heat they generate, it's pushed traditional data center infrastructure completely past its breaking point.
We're in a whole new world.
We really are.
Yeah.
We're operating in this landscape where the diagnostic waters aren't just murky, they are violently boiling.
Which brings us to exactly what we are dissecting today. Welcome to the deep dive. And we know you, the listener, could be coming at this from, a dozen different angles.
Right. Everybody has a different stake in this right now.
Exactly. Maybe you're prepping for a high-stakes IT strategy meeting, or maybe you're trying to evaluate this exploding AI infrastructure market, or, maybe you're just endlessly curious about how the internet's heaviest, most expensive workloads actually function behind locked doors.
Which is fascinating in its own right.
Totally. So whatever brought you here, consider this deep dive your cheat sheet to the future of the data center.
And our source material today offers a really rare look under the hood. We have an internal strategy and product deck for the Supermicro Software Management Suite.
And Supermicro obviously is a massive player in the hardware space. They build the physical boxes.
They do, yeah.
Yeah.
But this deck is entirely focused on their software orchestration layer.
Right, and their overarching mantra for this suite, which is plastered right on the front of the deck, is accelerate everything. So our mission today is to decode what that actually means.
That's a bold claim.
It really is. We want to understand the mechanics of how they're attempting to tame this overheating, chaotic, and just incredibly expensive world. Because the picture they paint of a data center operating without this kind of overarching software, it's really bleak.
Oh, it outlines a complete operational nightmare.
Yeah.
We were talking about highly paid infrastructure engineers spending days just manually configuring servers.
Like clicking through menus one by one.
Yeah. And we're looking at fragmented security postures where, critical alerts have no centralized root cause analysis, exactly like your 2.0 coolant leak scenario.
Nobody knows what's actually broken.
Right. And perhaps most painfully, the deck shows end-user developers. So the data scientists who are actually building the AI models, waiting in line for days or even weeks just to get access to the hardware.
Just to run a single test.
Exactly. The bottlenecks are everywhere.
So how does Supermicro propose to stop the bleeding here? The big architectural philosophy they introduce in this deck hinges on this very specific phrase: independent but integrated.
Yeah, that phrase is basically the crux of their entire go-to-market strategy. It's a modular architecture.
Okay, modular. Break that down for us.
So they've built 4 distinct software modules that cover the entire life cycle of an AI workload. We're talking from the physical power cables all the way up to the developer's code. But, and this is crucial, They state that a customer does not have to buy the whole ocean.
You don't have to rip and replace everything you own?
Right. You can adopt just the monitoring piece or maybe just the developer portal without being forced into a single platform dependency.
Okay, I want to test an analogy on you here.
Sure. Here.
In the consumer world, this sounds a lot like the difference between buying a really high-end component-based stereo system versus buying an all-in-one boombox.
Okay, I track with that.
Right. So with the stereo system, you have discrete parts. If you want a punchier amplifier, you buy a new amp. You upgrade the turntable, you swap out the speakers. And they all talk to each other through, like, standard RCA cables.
It has an analog setup, yeah.
Exactly. But the all-in-one boombox, I mean, it might be easier to carry out of the store, but the second the CD player jams, the entire unit becomes a heavy, useless piece of garbage.
I see where you're going. But, and this is a big but, here's where that analogy actually breaks down in the enterprise IT space.
Oh, how so?
Well, in your stereo example, the RCA cables are a universal standard.
Right.
Everyone agreed upon them decades ago. Sony amps work with Pioneer speakers.
Right, it's just plug and play.
Exactly. But in software-defined data centers, those standard cables don't naturally exist. Historically, if you bought a monitoring tool from vendor A and, say, an automation tool from vendor B, they absolutely did not speak the same language.
Ah, they're completely siloed.
Completely. You had to spend months paying developers to write custom API bridges just to get them to share basic data, like, hey, tell the other software the server's on.
So you're saying the IT industry's version of the boombox, that monolithic all-in-one vendor suite, it existed because it was the only way to guarantee the parts would actually communicate with each other?
Precisely. Vendors intentionally built monolithic suites to create vendor lock-in. I mean, they want you to buy their boombox.
Right, because once you rely on their proprietary orchestration layer, you're just trapped.
You're financially and operationally trapped. Switching away costs way too much time and money. But what this source material claims is that Supermicro has built the individual stereo components to function entirely on their own.
Okay.
But if you do plug them all together, they automatically recognize each other and form a single unified nervous system. They claim they've solved the API bridge problem right out of the box.
Okay, but I have to play the skeptic here for a second.
Please do.
If I'm the chief information officer, right, and my current data center is already this tangled mess of 30 different software tools, doesn't buying 4 separate modules from Supermicro, even if they promise integration, doesn't that just add more puzzle pieces to an already messy table? I mean, am I not just buying more fragmentation?
That's a totally valid fear, and the text anticipates that exact pushback. The deck emphasizes that this modularity specifically mitigates operational and security risks.
How does having more pieces mitigate risk?
Think about it like a ship with watertight compartments. If a massive zero-day vulnerability is discovered in one vendor's monolithic platform, your entire data center is compromised. The whole ship sinks.
Oh, right, because it's all one connected brain.
Exactly. By decoupling the architecture, you isolate your risk domains. But to your point, the burden of proof is heavily on Supermicro to prove that the integrated part of independent but integrated actually works in practice.
Well, let's put that to the test then. Let's walk through the anatomy of an AI data center crash and see how this suite actually responds to it.
Let's do it.
We have to start at the absolute foundation. We need to go down to the concrete floor, under those raised tiles, to the physical layer. The blinking lights, the thick power cables, the liquid cooling pipes.
The heavy metal.
Yeah. Because if you cannot observe the physical reality of your hardware, every software abstraction you build on top of it is just flying blind. Which brings us to the first module in the suite, SuperCloud Composer.
SuperCloud Composer, or SCC. The text defines this as the unified observability and policy-driven monitoring layer.
Observability, that's a buzzy word right now.
It is, but to understand its real scope here, we need to look at what it's actually pulling data from. It isn't just like pinging a server to see if the operating system is awake.
Right, it's not just a heartbeat check.
No, SCC is deeply integrated into the physical hardware. It monitors compute, GPU, network, storage, but crucially, and this is big for AI, it monitors power and cooling down to the individual component level.
The source material specifically mentions it uses standards-based telemetry, highlighting this thing called redfish. Now, for those who haven't spent their weekends reading server management protocols...
Which is most people,
Well,
honestly.
Right. What exactly is redfish, and why does it matter so much that it's open?
Redfish is a critical piece of context here.
Yeah.
So, historically, every server manufacturer, whether it's Dell, HP, or Supermicro, they all had their own proprietary language for talking to the BMC.
The BMC, what's that?
The baseboard management controller. It's basically a tiny independent computer built directly into the motherboard that controls the server's physical hardware. It has its own network connection, its own little processor.
So even if the main computer crashes, the BMC is still alive.
Exactly. But in the past, if you wanted to check the fan speed or the temperature on a proprietary server, you needed that specific vendor's proprietary software to talk to their BMC.
So if you had a mixed data center, you were running 5 different monitoring tools.
Yes. It was awful. Redfish is an open industry standard that fixes this. It's a RESTful API, meaning it uses standard web protocols that any developer can easily work with.
Oh, nice.
By building SCC on Redfish, Supermicro is proving they aren't trying to lock you into their hardware. SCC can theoretically monitor a rack of Dell servers just as easily as it monitors a rack of Supermicro servers.
Okay, that's huge. And it takes all that data and feeds it into dashboards. The text mentions native integrations with Prometheus and Grafana.
Yes, which are basically the gold standards in open source observability right now.
How do they work together?
So Prometheus is the engine that constantly scrapes the time series data, meaning it's recording the exact temperature of a GPU every single second and storing it chronologically.
It's the historian.
Exactly. And then Grafana is the visualization layer. It takes millions of rows of boring temperature data from Prometheus and turns it into those beautiful reader line charts on the operator's screen.
Okay, so SCC gives us the God's eye view. We can see everything. But let's go back to our 2.0 AM coolant leak scenario. The pipe bursts, the fluid hits the rack. How does SCC actually handle that chaotic flood of alerts we talked about? Does it just, make a prettier chart of my servers dying?
And that is exactly where we move from passive observability to what the deck calls policy-driven automated actions. This is the active remediation engine.
Active remediation, so it fights back.
Right. In your scenario, without SCC, the human operator is trying to manually parse the noise. But with SCC, you have predefined policies. When the system detects the signature of a coolant leak,
What would a signature look like?
it would look like a sudden drop in pressure in the coolant distribution unit, paired simultaneously with a rapid temperature spike on the specific GPUs in that rack.
Ah, so it cross-references the data.
Exactly. And when it sees that pattern, it doesn't wait for a human to click a button.
It takes action.
Immediate action. The text explicitly states it can disable smart PDU outlets to isolate affected equipment.
Wait, let's unpack the mechanics of that. It literally cuts the power to the specific outlet on the physical rack. It just hard kills the electricity.
It can, if that's the policy you set.
Oh.
But the nuance here is crucial if you want to avoid massive data corruption.
Right, because yanking the power cord on a database server is usually a terrible idea.
It's catastrophic.
Yeah.
You don't usually want to just kill the power on a GPU that is right in the middle of writing data to storage. So the deck mentions it can execute remediation scripts or trigger a graceful shutdown.
So what does a graceful shutdown look like in this emergency?
A properly configured SCC policy would first talk to your orchestration layer. It would instantly cordon off that server so no new workloads get sent to it.
Makes sense. Stop the bleeding.
Then it tells the running applications to save their state and migrate to a healthy server in another rack. And then, once the data is safe, it signals the PDU to cut the power.
Wow. So it's not just a blind reflex, it's a coordinated evacuation.
Exactly.
It's like pulling your hand away from a hot stove, but making sure you don't drop the expensive glass you're holding before you do it. That is incredibly sophisticated.
It has to be. At the scale of modern AI, human reaction time is simply too slow to prevent millions of dollars in hardware damage.
Okay, let's shift gears slightly within Composer, because there's a feature in here that genuinely stopped me in my tracks when I read it. It's a section on power tracking, and it talks about monitoring something called PUE, power usage effectiveness.
Oh, PUE is the ultimate metric for data center efficiency.
Can you walk us through the math on that?
The math is relatively simple, actually. You take the total amount of power entering the building, and you divide it by the amount of power actually used by the IT equipment, so the servers and switches.
Okay, so if a facility draws 100 megawatts total, and 100 megawatts goes directly to the servers, your PUE is a perfect 1.0.
Right, but that's physically impossible.
Because you have to run the cooling systems, the lights, the security cameras, the coffee maker, and the break room.
Exactly. The cooling is the biggest drain. So a PUE of 1.5 means that for every 1 watt of power used to compute data, you are spending half a watt just to keep the building running.
Mostly on air conditioning.
Yes. So getting that number down to like 1.2 or 1.1, is the holy grail of data center engineering.
And the deck highlights that SCC tracks this really granularly, not just at the facility level, but down to the per GPU power draw using in-band telemetry. But here's the part that threw me.
What's that?
There is a diagram in the source material outlining a feature called Power Asset Orchestration. And it shows Composer connected not just to the servers, but to the commercial grid.
Yes.
And right next to it, it shows a private smart grid with little icons for solar panels and battery storage. Why is a software suite designed to manage servers deeply concerned with the solar panels on the roof? Shouldn't it just care about the electricity once it hits the rack?
That is the traditional way of thinking for sure. But AI has completely broken that paradigm. To understand this, we really have to look at the macroeconomics of energy.
Okay, let's go there.
Training a massive language model doesn't just use a lot of power. It uses an unprecedented density of power. We are talking about single facilities drawing hundreds of megawatts. That is enough electricity to power a medium-sized city.
Right. I mean, there are stories about data centers literally straining local municipal grids, like towns are worried about brownouts.
Because of that immense draw, data centers are no longer just passive consumers of electricity. They have to act as major players in the energy market. The text links this power asset orchestration feature to cost and carbon-aware power optimization and peak shaving.
Let's break down peak shaving. That basically means avoiding power usage when the commercial grid is charging the highest rates, right? Like during a massive heat wave when everyone in the city turns on their air conditioning.
Correct. On the commercial grid, power prices fluctuate in real time based on supply and demand. If a data center is running at absolute maximum capacity during peak demand, their energy bill will be astronomical.
It would ruin their margins.
Completely. What Supermicro is demonstrating here is that the software managing the servers must now be intelligent enough to negotiate with the energy grid.
So, practically speaking, if the commercial grid price spikes at 3:00 p.m., what does SCC actually do?
It acts as an autonomous energy broker.
Really?
Yeah. Through power asset orchestration, SCC can detect that price spike. It can then dynamically shift the data center's power source. It might command the facility to start pulling from its on-site lithium-ion battery reserves, or maybe maximize its draw from its dedicated solar array.
Just seamlessly switching the power source.
Seamlessly.
Yeah.
And if that's not enough to offset the cost, it can actually throttle the IT load.
Wait, it can tell the servers to slow down?
Yes. It can pause non-critical background compute tasks.
Or
Or it can slightly lower the clock speed of the CPUs and GPUs across the fleet to reduce total power draw until the grid prices stabilize.
That's incredible.
It is integrating facility management, the physical building's energy strategy, directly with IT workload management in a single unified control loop.
That is a staggering level of integration. The server software is essentially watching the global energy market.
It has to, just to survive.
All right, so let's check our progress here. SuperCloud Composer is our foundation. The hardware is continuously monitored, it's protected from catastrophic physical failures, and it's optimizing its power consumption based on grid pricing.
The physical layer is rock solid.
Exactly. The machines are physically healthy, but right now they are completely brainless. They are just incredibly expensive, very safe hunks of metal with no operating systems.
Which brings us to the next massive bottleneck in the data center lifecycle: provisioning.
Right, because if I have 10,000 new bare metal servers sitting in racks, I cannot have a team of IT guys walking around with a USB stick and a crash cart monitor, plugging into each server to install Windows or Linux.
No, you definitely cannot. And yet, the way many enterprises handle this today isn't much better than the USB stick. Well, the text calls out the specific pain points of the current landscape: fragmented consoles, inconsistent automation standards, and zero single control points for execution.
Which introduces the second module in the suite, SuperCloud Automation Center, or SCC. I'm going to call it the orchestrator.
The orchestrator is very accurate. SEC's primary mandate is infrastructure automation. It handles everything from bare metal provisioning and firmware orchestration to the final cluster deployment.
But the deck makes a statement here that feels almost counterintuitive for a company trying to sell you a massive software suite. It says, SCC doesn't replace tools, it orchestrates them.
Yeah.
If they're trying to sell me automation software, why wouldn't they want to replace my existing automation tools? Wouldn't that make them more money?
Because replacing an enterprise's existing automation code is a non-starter. It would be commercial suicide.
Why?
To understand why, you have to realize that large IT departments have spent years and millions of dollars writing infrastructure as code.
Okay, let's define that term for the listeners. Infrastructure as code.
It means instead of a human manually clicking through menus to configure a server, they write a script, a piece of code, that defines exactly what that server should look like.
It's like a recipe.
Exactly like a recipe. It defines the operating system, the network settings, the user permissions. They use tools like Terraform to define the desired state of the infrastructure, and tools like Ansible to go in and configure the specific software packages.
So my team has this massive library of Ansible playbooks and Terraform plans that perfectly describe our specific corporate environment.
Right. Decades of institutional knowledge baked into those scripts.
And if Supermicro came in and said, hey, throw all that away and use our proprietary drag-and-drop tool instead, I would laugh them out of the building.
Exactly. The switching cost is way too high. So SCAC takes a really brilliant architectural approach. It sits on top of the open source tools you already use.
It doesn't fight them.
No, it embraces them. The text lists native integrations with Ansible, Terraform, Chef, Puppet, and XHAT. SK acts as the overarching state machine. It dispatches tasks to these specific tools via components they call SK workers.
So here's how I'm visualizing this. Imagine building a massive commercial skyscraper.
Okay, I'm with you.
SK is not the electrician, and it is not the plumber. The electrician is Terraform, and the plumber is Ansible. SK is the master general contractor.
Oh, that's a perfect analogy.
Right. The GC doesn't pick up a wrench, but they hold the master blueprint. Their job is to ensure the plumber finishes laying the pipes on the 40th floor before the drywall team shows up to close the walls. SA ensures all these disparate scripts run in the exact correct chronological sequence.
And in an AI data center, that order of operations is staggeringly complex.
Okay.
The text points out that SA handles multi-step actions across the entire stack.
Where does it start?
It starts at the absolute bottom, the BIOS. That's the foundational firmware that tells the motherboard how to talk to its own components. Then it configures the BMC, which we talked about earlier.
Okay, so the hardware is awake?
Then it moves up a layer to provision the actual operating system. Then it lays down the platform layer, like installing the Kubernetes cluster. And finally, it can deploy the AI application itself.
That is a massive chain of dependencies. I mean, if step 2 fails, step 5 is going to cause a catastrophic crash.
Which is why the fleet-wide actions detailed in the text are so vital. We aren't just doing this to one single server, we are doing it to thousands simultaneously. SCIP performs fleet-wide firmware baselining.
Baselining, meaning it guarantees every single server is running the exact identical software version.
Yes, down to the smallest patch. If you have a cluster of 1,000 GPUs training a model together, and one single server has an outdated version of a network interface driver, it can cause microstutters in data transmission.
And does that really matter?
It matters immensely. Those microstutters can slow down the entire $100 million training run because the other 999 GPUs have to pause and wait for that one slow server to catch up.
Oh, wow.
So SK offers version pinning and drift detection to prevent that.
Drift detection. So if, say, a rogue IT admin logs into a server in the middle of the night and manually updates a driver trying to fix a bug, and that breaks the baseline, SCAC catches it.
It flags it immediately because the server has drifted from the approved infrastructure code. It alerts the team or can even automatically roll it back.
That is robust. I also noticed SCAC specifically notes support for non-PXE and non-DHCP environments for OS provisioning.
Yes, that's a critical security feature.
We need to clarify those acronyms for everyone.
Yeah.
PXE, often pronounced PXE, and DHCP. What are they, and why is it actually a feature to not use them?
PXE stands for Pre-Boot Execution Environment. Combined with DHCP, which automatically assigns IP addresses, it's the traditional easy way to boot a blank server over a network.
How does it work normally?
You plug in a new server, it wakes up, asks the network, hey, what's my IP address? And then it automatically downloads its operating system from a central server.
Sounds incredibly convenient. Why wouldn't you want that?
Because in highly secure, zero-trust environments, think like a government intelligence data center, or a massive financial institution broadcast protocols like DHCP are often completely banned.
Why?
They're considered massive security risks. A malicious actor who gets onto the network could theoretically intercept that traffic and feed a compromised operating system to a bare metal server right during the boot process.
Oh, so they compromise the machine before it's even fully awake.
Exactly.
Right.
By supporting non-PXE provisioning, SK allows enterprises to push operating systems onto bare metal using out-of-band management protocols, which is vastly more secure. It doesn't rely on broadcasting to the whole network.
Speaking of security, I want to drill down into a specific mechanism here, because I am still imagining that veteran IT admin who wrote all those Terraform scripts being very annoyed by this new SCAKE layer. You said it orchestrates their scripts, but what tangible benefit does the admin actually get day to day to make them like this tool?
The biggest immediate benefit for the admin is how SCAKE handles secrets management. The text highlights that SCAKE provides secrets injection centrally.
What is the mechanical difference between how secrets are handled with and without this system?
Okay, without SCAKE, if an admin writes an Ansible playbook to configure a database, that playbook needs the master password to access the database, right?
Right.
Often, out of laziness or just bad practice, admins will hard code that password directly into the text of the script, or they store it in a local text file on their laptop.
I've definitely seen that happen.
We all have. But if that laptop is compromised or the script gets uploaded to a shared Git repository, the entire database is compromised.
A massive vulnerability.
A critical one. With SCAKE, the admin removes the password from the script entirely. They store the master password safely inside SCAKE's encrypted digital vault.
Okay, but the script still needs the password to run. How does it get it?
When SCAKE triggers the Ansible playbook to run on a target server, it doesn't write the password to a file. Instead, the vault generates an ephemeral, temporary credential. It injects it directly into the running memory of the server just for the millisecond it's needed to authenticate. And then the token just evaporates. It's gone.
So even if a hacker steals the Ansible playbook while it's executing on the server, there is no password in it.
Exactly. It makes the IT admin's existing code exponentially more secure without them having to rewrite their underlying logic. Furthermore, it tracks the success or failure of all these executed scripts in a single unified dashboard, which completely eliminates the need for humans to coordinate over Slack saying, "Hey, did your script finish?"
Okay, the picture is really coming together now. Composer is monitoring the physical hardware and the power grid. Automation Center has laid down the exact baseline firmware, securely installed the operating systems, and configured the complex software dependencies.
The machines are humming, perfectly in sync.
But right now, this data center is basically a private island. It's fully functional, but it only has one owner. In the real world, computing power is a commodity that gets rented out.
It's all about multi-tenancy.
Right. If you are a major enterprise, you have dozens of different internal business units that need access to these servers. The marketing data science team should not be able to see the confidential algorithms being trained by the quantitative finance team.
Absolutely not.
And if you are a public cloud provider, you are renting these servers out to entirely different competing companies. We need to build walls. We need digital fences to divide up this massive physical infrastructure securely.
And this introduces the third pillar of the suite, SuperCloud Director, or SCD. The text explicitly defines this module as a multi-tenant bare metal control plane.
The digital landlord.
A very, very strict digital landlord. Its core function is to offer automated, network-isolated tenant infrastructure.
The source material is very specific about the architecture under the hood of Director. It says it is built on OpenStack building blocks, specifically highlighting OpenStack Ironic and OpenStack Neutron. I want to spend some time here because OpenStack has a fascinating reputation in the IT world.
Well, it certainly does. OpenStack is an open-source cloud operating system. It was originally created over a decade ago by NASA and Rackspace.
NASA?
Yeah. The goal was to allow anyone to build their own AWS-style cloud infrastructure right in their private data center.
But its reputation is that it is notoriously, agonizingly difficult to deploy and maintain, right? I mean, it's incredibly powerful. But the joke is that it requires a team of PhDs to keep it running.
Historically, yes, that is a very fair assessment. It's a massive, complex beast of a project. However, the code itself is incredibly battle-tested. I mean, it runs some of the largest telecommunications networks on the planet today.
So why is Supermicro using it if it's so hard to use?
By using OpenStack building blocks for SCD, Supermicro isn't trying to reinvent the wheel. They are taking this incredibly robust open-source engine and using their own software to abstract away all the painful deployment complexity that usually plays OpenStack.
They're putting a user-friendly wrapper around the beast.
Exactly.
Let's look at the specific pieces they use. The text mentions OpenStack Ironic for bare metal provisioning. Let's tackle that term. Bare metal.
It's a crucial concept here.
Because for the last 15 years, the entire enterprise IT world has been utterly obsessed with virtualization, virtual machines. You buy a massive server, you install a hypervisor like VMware, you slice that physical server up into 20 virtual machines, and you hand them out. Why is SuperCloud Director specifically focused on a bare metal control plane? Why are we going backwards and handing users raw hardware?
Because AI workloads have fundamentally different physics than traditional web applications.
How so?
Well, if you are hosting 20 different corporate blogs, virtualization is brilliant. It shares resources perfectly. But if you're training a massive language model, virtualization is a severe bottleneck. We have to look at the mechanics of a hypervisor.
Walk us through it.
A hypervisor is a layer of software sitting directly between the physical hardware and the user's operating system. Every single time the user's AI application wants to write a piece of data to memory or send a packet across the network or push a complex matrix calculation to the GPU, that request has to be intercepted, translated, and routed by the hypervisor.
It's a middleman.
A middleman. And even the most optimized state-of-the-art hypervisor using hardware pass-through introduces overhead. It might only be a 2% or 3% performance penalty.
Which, honestly, sounds negligible.
It sounds negligible until you scale it to AI proportions. If you are renting a cluster of 1,000 top-tier NVIDIA GPUs, you might be paying upwards of $50,000 an hour for that compute.
$50,000 an hour.
Easily. And these GPUs communicate with each other constantly over high-speed InfiniBand networks to synchronize their mathematical weights. If a hypervisor introduces even a microsecond of jitter or a 2% bandwidth penalty on the bus, it disrupts that delicate synchronization.
So they fall out of sync.
Right. And over a 3-month training run, that 2% overhead compounds into millions of dollars in wasted compute time.
Wow. Okay. I see the problem.
So for true, heavy-duty AI training, the tenant needs direct, unimpeded, microscopic access to the physical silicon. They need the bare metal. And OpenStack Ironic is the engine that securely hands over control of that physical server to the tenant.
Okay, but handing over the hardware is only half the battle. You have to make sure the tenants can't see each other. That's where OpenStack Neutron comes in, right?
Exactly. The text notes Neutron handles the automated network isolation, specifically mentioning VLAN and VXLAN technologies.
Let's talk about why you can't just put everyone on the same network and use strong passwords. If I hand a bare metal server to the finance team and another bare metal server in the exact same physical rack to the marketing team, why is it so critical they're on physically and logically isolated networks?
Because passwords and software locks are vulnerable to network sniffing and lateral movement. Think about what is actually being processed on these GPUs.
Highly sensitive stuff.
Incredibly sensitive. A major hedge fund might be constantly fine-tuning AI models using highly proprietary confidential trading algorithms and real-time market data. Or a healthcare conglomerate might be training diagnostic models using millions of raw, unencrypted patient medical records.
The data is the crown jewels. If it leaks, the company is ruined.
Or legally liable for billions of dollars. If both of those tenants are operating on a flat, shared network, sophisticated malicious actor who breaches the marketing team's server, maybe through a phishing email, could theoretically listen to the network traffic passing through the main switch.
And intercept the financial or medical data as it passes by?
Precisely. So how does Neutron prevent that? What is a VXLAN?
Yeah, explain VXLAN.
VXLAN stands for Virtual Extensible LAN. It is a highly advanced network encapsulation technique. In simple terms, Neutron wraps every single piece of data, leaving the finance team's server in a cryptographic envelope.
Okay, an envelope.
And that envelope can only be opened by other servers, specifically assigned to the finance team's isolated network. Even though the data is physically traveling over the exact same copper cables and network switches as the marketing team's data, they are cryptographically invisible to each other.
It creates a secure tunnel through the shared physical space.
Exactly. The source material refers to this as creating secure infrastructure partitions for sovereign or regulated tenants.
Sovereign is the key word there, isn't it?
Yes, a sovereign tenant, like a government defense agency or a heavily regulated European bank, they require mathematical certainty that their data is completely isolated. They demand total data sovereignty.
And SuperCloud Director automates the creation of these mathematically isolated mini data centers inside the larger physical facility.
It does. It builds the walls automatically.
All right, let's take a breath and look at the whole board here. We have Composer monitoring the heartbeat and the power grid. SAC has orchestrated the firmware and operating systems perfectly. Director has carved up the data center into secure, bare metal, isolated fortresses for our different tenants.
The infrastructure is flawless.
From an infrastructure perspective, the job is done, the data center is perfect, but It is entirely useless until someone actually runs code on it.
The most important part.
Right. We have built the ultimate racetrack, but there are no drivers in the cars. And historically, getting the drivers into the cars is the most frustrating part of this entire industry.
It is notoriously the most broken relationship in enterprise tech. The friction between the IT operations team who controls the hardware and the development team who actually builds the software.
And this brings us to the final and frankly the most fascinating module in the suite, the interface for the end user, SuperCloud Developer Console, or SDX.
Yes.
I called Director the digital landlord. I'm going to call SDX the AI vending machine.
The AI vending machine is a very fitting analogy because the core problem SDX is trying to solve is a massive bottleneck of human waiting. The text identifies the specific pain point. Developers rely on ops for environment setup.
Anyone who has worked in software engineering knows this pain intimately. It is the tyranny of the IT ticketing system.
Oh, the dreaded Jira ticket.
Exactly. A data scientist gets a brilliant idea for a new machine learning model. They need a specific environment. They need Python 3.Mayo. They need a very specific version of the NVIDIA CUDA drivers to talk to the GPU. They need PyTorch installed, and they need access to 4 GPUs.
Very specific requirements.
So they write up a Jira ticket and submit it to the IT operations team.
And then they wait.
They wait days, sometimes weeks, because the ops team is backed up dealing with the coolant leak we talked about earlier.
Right, they have bigger fires to put out.
So the developer loses their momentum, their brilliant idea just sits on ice.
And from the operations side, the tech nuts, they suffer from a different but equally painful problem. Poor visibility and infrastructure usage.
Because what happens when that developer finally gets their server after waiting 2 weeks?
They hoard it.
They hoard it like a dragon with gold.
This is a well-documented psychological behavior in engineering teams. Because the developer knows exactly how painful it is to wait in line for hardware, they ask for way more than they actually need.
Just in case.
Just in case. They request an entire server with 8 80-gigabyte GPUs just to test a very small, lightweight algorithm. And when they go home for the weekend, they leave the server running and allocate it entirely to themselves, doing absolutely nothing, just so they don't have to submit a new ticket on Monday morning.
Which means the company is burning tens of thousands of dollars in power and depreciation on idling GPUs, while other developers are stuck in the queue.
It is a total lose-lose scenario. Devs are furious because they are slow, and ops is furious because they are burning cash with terrible utilization rates.
So how does the AI vending machine fix human psychology?
By entirely removing the human from the provisioning loop. SDX is a Kubernetes-native AI platform. It offers a self-service portal directly to the developer.
Okay, so the data scientist logs into a web interface, sees a menu of available resources, selects, I need a PyTorch environment with 2 GPUs, clicks launch, and the system just dispenses their workspace instantly.
Instantly. It leverages Kubernetes, which is the industry standard for container orchestration, to instantly spin up a secure containerized workspace, preloaded with all the exact drivers and libraries the developer needs.
So they're coding in minutes, not weeks.
Exactly. But the real magic of SDX, the actual technical achievement that makes it an enterprise product rather than just a nice dashboard, is how it handles the underlying hardware, specifically a feature called GPU slicing.
This is where the deck gets highly technical. There is a visual showing a massive top-of-the-line 80 GPB GPU, and it shows SDX dynamically doing completely different things with it depending on what the developer asks for.
Because flexibility is the only way to maximize utilization. Let's say a developer is just using a Jupyter notebook to write some experimental code, or they're doing lightweight inferencing.
Inferencing meaning they aren't training a model from scratch. They are just asking an already trained model a question to see how it responds.
Exactly. For that, they do not need the immense power of a full 80 GB GPU.
Right. Handing them the whole GPU is like renting a 50-seater commercial passenger bus just so one guy can drive himself to the grocery store. It's a massive waste of seats.
That's a great way to put it. So SDX uses a time-sharing scheduler and spatial partitioning to slice that single physical GPU into multiple, smaller, fractional GPUs.
Let's break down the mechanics of that. How do you physically slice a microchip?
You are dividing its 2 primary resources, compute and VRAM, or video RAM. The software essentially tells the hardware, okay, developer A gets 20% of the compute cores and 16 gigabytes of the memory. Developer B gets 40% of the cores and 32 gigabytes of memory.
So they don't step on each other's toes.
Right. The developers experience this as having their own dedicated smaller GPU, but in reality, SDX is packing multiple developers onto the same physical silicon simultaneously.
It's an algorithmic rideshare. It dynamically fills every single seat on the bus to ensure the hardware is running at 100% efficiency.
And conversely, if a specialized team is doing massive LLM-distributed training like really building a foundational models from scratch, they need more than one bus. They need a massive fleet.
Right. They need hundreds of GPUs.
The text highlights single-node multi-GPU and cross-node multi-GPU allocation. SDX can seamlessly bind together dozens or hundreds of GPUs spanning across multiple physical bare metal servers and present them to the developer's workload as if it were one single massive supercomputer.
It abstracts the complexity away from the developer. They just write the code.
Exactly. But here is where we get to the absolute cornerstone of Supermicro's strategy, the massive differentiator that they believe makes this entire suite undeniable.
Okay.
The text emphasizes one core principle: vendor agnosticism.
This is the strategic crux of the entire presentation, isn't it?
It really is. SDX is designed to support multi-vendor accelerators. It explicitly calls out support for NVIDIA GPUs, AMD accelerators, specifically mentioning Ryzen and Intel Gaudi chips.
Which brings us to the most aggressive slide in the whole deck, the competitive analysis matrix, the smackdown slide.
Oh, they definitely came out swinging.
They compare SuperCloud Developer Console directly against two massive incumbents in the space, Run.ai and OpenShift AI. I want to heavily scrutinize this because obviously this is Supermicro's internal marketing deck. They are going to paint themselves in the best possible light. But the claims here are bold. Let's walk through the dimensions they chose to highlight.
The first dimension is vendor lock-in. The text asserts that both competitors have a high degree of lock-in.
How so?
Well, Run.ai is deeply embedded in the NVIDIA ecosystem. It relies heavily on NVIDIA's proprietary-based command manager. OpenShift AI is a Red Hat product, and Red Hat's entire business model is bringing you into their proprietary enterprise Linux and Kubernetes ecosystem.
Right. SDX, in contrast, claims zero lock-in, noting it is both hardware agnostic and Kubernetes agnostic.
Meaning you aren't forced to use a specific flavor of Kubernetes. You can run SDX on upstream open source K8s or Canonical or Nutanix. It plays nice with everyone.
Okay, what about the GPU sharing we were just talking about?
For GPU sharing, the matrix claims Run.ai offers limited support, mostly static allocation or relying on NVIDIA's MIG technology.
Let's define MIG quickly.
MIG is a multi-instance GPU. It's a hardware-level feature built by NVIDIA to slice their chips. The problem is MIG only works on very specific top-tier NVIDIA enterprise chips, and it partitions the GPU in very rigid, inflexible sizes.
So it's not as dynamic as the spatial partitioning you mentioned earlier.
No, it's quite rigid. OpenShift AI is also listed as having limited support for dynamic slicing. SDX, however, claims full dynamic partitioning for both NVIDIA and AMD.
Okay, moving down the matrix. Billing. This is crucial if we are acting as a digital landlord, right?
Absolutely. The text highlights that SDX features built-in token-based billing and FinOps capabilities. It mentions integrating with VLLM for precise API usage tracking. It claims the competitors have either no native support or only partial support, forcing customers to buy third-party billing tools.
Let's explain FinOps in this context. If I am the IT director and I have given the marketing team access to the AI vending machine, I need to know exactly how many tokens or GPU hours they consume so I can charge their departmental budget at the end of the month.
That's called a showback or chargeback model.
Right, because if the platform doesn't have native billing, I'm just guessing how much money marketing spent versus finance.
Precisely. Built-in billing is a mandatory feature for enterprise accountability. Otherwise, budgets just spiral out of control.
And then the final blow in the matrix, pricing. The slide shows SDX is priced at a competitive 1x, while they claim Run.ai and OpenShift are 3x to 3.5x higher in software licensing costs.
Quite a price gap.
Okay, I have to step in here and throw a flag. We are reading a corporate product deck. Of course, they put themselves as the cheapest, most feature-rich option with zero lock-in. It almost looks too good to be true. If SDX is a third of the price, supports all hardware dynamically, and has built-in FinOps, what is the catch? Why aren't the competitors doing this? Why are Run.ai and Red Hat so locked in?
That is exactly the right lens to view this through. To understand why the matrix looks like this, you have to examine the fundamental business incentives of the companies involved.
Follow the money.
Always follow the money. Building a truly hardware-agnostic platform is incredibly difficult and expensive from a software engineering standpoint. Companies like NVIDIA and Red Hat have built walled gardens by design. It's not a bug. It's their business model.
Because they want to trap you.
NVIDIA wants you to rely on their proprietary software orchestration layer so that next year, when it's time to upgrade your data center, you are technically forced to buy NVIDIA GPUs again. Red Hat wants you deeply embedded in OpenShift so you continuously pay their massive enterprise support contracts. They have no financial incentive to make it easy for you to use an AMD chip.
So why is Supermicro financially incentivized to be the good guy here? Why make it open?
Because Supermicro is, at its core DNA, a hardware server manufacturer. They are the Switzerland of AI infrastructure.
Ah!
They build and sell servers that contain NVIDIA chips, but they also build and sell servers that contain AMD chips and Intel Gaudi chips. The primary revenue driver is moving massive amounts of metal.
They just want to sell the physical boxes.
Exactly. Their ultimate incentive is to sell you as many physical servers as humanly possible, regardless of whose silicon is sitting on the motherboard. Therefore, they are uniquely financially motivated to build a software orchestration layer, this independent but integrated suite that completely removes the friction of using any hardware.
Wow. Okay. The strategy snaps into focus. They are heavily discounting the software, selling it at 1x, and making it hardware agnostic because the software isn't their primary cash cow.
No, it's a loss leader.
Or at least a margin compressor, designed to make buying their physical servers an absolute no-brainer. They make the software frictionless so you buy the metal.
That is the architectural and commercial reality of this suite.
Let's bring this all together. Let's synthesize this journey we've just taken through the anatomy of the data center. We started in the chaos of the physical layer. We used the SuperCloud Composer to bring order, monitoring the thermal limits, executing graceful shutdowns before hardware melts, and actively negotiating with the power grid to lower costs.
Then we moved to the SuperCloud Automation Center, the general contractor.
Right. We used it to securely vault our passwords, inject them dynamically into memory, and orchestrate the insanely complex fleet-wide deployment of firmware and operating systems without ever touching a USB drive.
Next, we erected the digital walls with SuperCloud Director. We leveraged battle-tested OpenStack components to carve out mathematically secure, zero-overhead bare metal environments for sovereign tenants.
And finally, we solved the human bottleneck with the SuperCloud Developer Console. We gave the data scientists an AI vending machine, allowing them to dynamically slice hardware, bypass the IT ticketing queue, and actually focus on building models while the FinOps engine tracked the budget.
It's a complete life cycle.
So stepping back from the technical weeds for a second, what does this all mean for you, the listener? Why should you care about this internal product strategy? If you are a business leader, a CIO, or an investor managing an IT budget, this source material crystallizes a fundamental truth about the current AI boom. Buying the GPUs is simply not enough. It is the easy part.
It truly is. I mean, if you spend $50 million on a cluster of top-tier accelerators, but they are sitting idle 40% of the time because your developers are trapped in a Jira queue, or because they can't efficiently time-slice the hardware, you are actively burning shareholder capital.
Is lighting money on fire.
At the scale of modern AI, sophisticated software orchestration is the only mathematical way to achieve a real return on investment on the hardware.
And if you are an end user, a developer, or a data scientist, this deck represents a future where the friction is finally removed. It's a future where you are unblocked. You can summon immense multi-node compute power instantly, iterate on your neural networks at the speed of thought, and treat the data center as a seamless extension of your own laptop.
I think what this Supermicro suite fundamentally reflects is the maturation of the AI industry as a whole.
How so?
For the last 3 years, we have been in the Wild West phase. Companies were just buying whatever GPUs they could get their hands on, plugging them in, and dealing with the chaos. We are now officially entering the enterprise-grade, highly managed, secure, and aggressively cost-conscious phase of AI infrastructure.
The infrastructure has to grow up to support the scale of the ambition. And this text is a blueprint for exactly how that maturation happens under the hood. Now, before we wrap up, I want to leave you with one final provocative thought, something to chew on that builds on the mechanisms we've discussed today.
I like where this is going.
Early on, we took a deep dive into Composer's power asset orchestration, the ability for the data center software to track real-time grid energy pricing and dynamically shift loads between the commercial grid, solar arrays, and battery storage.
Right. It was negotiating with the energy markets to perform peak shaving.
Now, mentally combine that capability with SDX, the developer console that acts as the overarching brain scheduling the actual AI workloads. What happens when the system scheduling the AI directly communicates with the system monitoring global energy prices?
Oh, the data center essentially becomes an autonomous energy trader.
It's an inevitable evolution. Imagine a scenario next year. A massive trillion-parameter AI model is halfway through a month-long training run. Suddenly, a severe heat wave hits the region. The commercial grid is strained, and the price per kilowatt hour skyrockets.
Right, power gets incredibly expensive.
Without human intervention, the data center's integrated software detects the price spike. It autonomously calculates that continuing to train the model at full speed for the next 3 hours will destroy the monthly budget. So the orchestration software automatically signals the Kubernetes cluster. The cluster tells the AI model to gracefully pause its training and checkpoint its data. The hardware spins down into an ultra-low power state.
It just goes to sleep.
It goes to sleep and it waits. It waits until the software detects that the facility's solar panels have caught the afternoon sun, or it waits until 11:00 p.m. when the commercial grid rates drop back down to off-peak pricing. And then, autonomously, it wakes the hardware back up, reloads the model into memory, and resumes training exactly where it left off.
So the system is optimizing its workload, not just for time, but for carbon footprint and financial cost, in real time, completely autonomously.
It means the future of AI isn't just about raw computing power. It is going to be deeply, inextricably entangled with the future of global energy markets. The AI infrastructure will learn how to feed itself based on macroeconomic conditions.
The software isn't just managing the server anymore, it's managing the physical reality of the world around the server.
That is a staggering paradigm shift. The diagnostic X-ray might look murky when you first glance at a modern data center, but once you apply the right observational and orchestration tools, you realize it's not just a collection of fragile hardware, it is a living, breathing economic ecosystem. Something for you to ponder until our next deep dive.